Hey there. Today we're going to look at proving triangles are similar. Remember, for triangles to be similar, all of their angles have to be congruent. Their corresponding angles are congruent, and their corresponding sides are going to have the same ratio. We call that proportional. So when you look at this, okay, are these similar or not? Well, they kind of look similar. Remember, same shape, different sizes, but we'd have to be able to, other than just looking at it and say, yeah, it looks like it, I'd have to be able to prove that. And if you look at it, let's start with the angles. They've given us a couple angles, but really they only gave us two, but I think we could figure out that third angle, couldn't we? If this is a 60 and this is a 50, what would this one up top have to be? Well, you got to subtract from 180. 180 minus 60 minus 70 ends up getting me 70 degrees. Okay, so I have that third angle. But over here, wouldn't that also be the case? It's the same measurements, so wouldn't this also be a 70? So I do have all three angles matching up like I want them to. Are the sides going to be proportional too? Let's look into it. Actually, yeah, they are. Okay, so this is actually, just like we have special ways to prove triangles congruent, like you don't have to show everything's congruent, you can just do side angle side or side side side. Same deal with similarity. I don't really have to show everything. I don't have to show every angle congruent and every side proportional. We have some shortcuts. This one is called angle similarity, and it is what I just showed you. If you know two angles are congruent, you automatically know that the third angle is going to be congruent. That's called the third angle theorem, actually, from a chapter or two ago. The third angle theorem would say that those are congruent. And then you have the three angles congruent, but ultimately all I had to be given was two angles congruent. We call it angle similarity. See the little similar sign? All right, then I know my triangles will be similar. Okay, so let's look at this. They give us a couple triangles. Are they similar? Well, I don't know. Do we have angle? I see that I have a 90 degree and a 90 degree. The other two angles don't match though. But I should probably check and see, does the third angle match anything? So I'm going to do 180 minus 90 minus 39. And I end up getting a 51 for this angle right here. And on this second triangle, if I were to do 180 minus the 90 minus the 51, I end up with a 39 is what that ends up being. So I actually do have angle similarity here. It didn't look like it, but I could figure it out that it does end up with the angles all the same. So I'm going to say yes, angle similarity. Let's try this next one. It's a little bit different. Looks like I've got isosceles triangles, though they're not the same size. One's bigger. That's why you see the double hash mark versus the single hash mark. Okay, they've only given us one angle, but we do know that in an isosceles triangle theorem, if the sides are the same, then the base angles are. So this is 68, this is also 68. And then I could do 180 minus the 68 minus the 68 to see what my vertex angle is. So let's see what we get. 180, 68 minus 68. I get 44 for a vertex angle. Okay, so then when I look at my other triangle here, they've actually given me the vertex angle. This 62, you can see these are the congruent sides, so this and this angle are going to be my base angles that are congruent. This is my vertex angle, it's 62. This vertex angle, 44. Ain't going to happen. I would say no on this one. They don't have the congruent angles that I need. Angle similarity is not the only one that works. There's a few more, and I'm not going to spend a lot of time proving why these work, but here they are. Side angle side similarity. Now that's not the side angle side we're used to, because side angle side would show that triangles are actually congruent. When we say side angle side similarity, we mean we have a set of sides that have the same ratio as another set of sides. Okay, so we've got two sides proportional, not congruent. Two sides proportional, and then you have the angle congruent. It does have to be the angle between the two sides, so where it goes side, then angle, then side. All right, we also have side similarity. If you can show all three sets of sides have the same ratio, then that's enough to show that they are similar. All right, so let's try those. This looks like I would be checking my side, 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 because they've given me side measurements here. Now, you always want to make sure that you sometimes will like rearrange and rotate and flip this triangle. So I always pick like the smallest, then the medium, then the largest sides and set them up. So I'm going to go small triangle to big triangle. So I'm going to start with this one. And that's going to be my numerator. So I'm going to say 6 is the smallest to the smallest side in the right in this triangle. So 6 to 9 equals, and this is really an equal side with a question mark. I don't know if it's equal. That's what I'm just checking. Then the medium length. In the smaller triangle that's 8, the medium length is a 12. And does that have the same ratio as, then let's do the long side. So in the little one it's 10, and the big one, the long side is 15. And now what I do is I check each one of those ratios. Sometimes they're nice fractions. These actually are really nice fractions that can reduce, but they're not always. So I'll show you, probably I would just do a decimal on it. I would just do 6 divided by 9. That is a 0.6 repeating. Now I'm going to check each one of these fractions. What's 8 divided by 12? Oh, it's also 0.6 repeating. And 10 divided by 15? Also 0.6 repeating. If those decimals are all the same, then those ratios are all the same, meaning the sides are proportional. I'm going to go side, 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 similarity. That worked. If I got 2 of them to be the same and the third one different, not going to work, not going to be similar. All right, next picture. This is a little bit sneaky because it's like overlapping triangles. You have this, that triangle, compared to the bigger triangle here that's, so this little piece here isn't really anything. It's like a little triangle lying right on top of this bigger triangle. All right, so then we have to compare. If it helps you, go ahead and separate out your triangles. You can make a triangle that looks like this. Let me see if I can make these line up right. Where this is 8 and this is 12, and I don't know what this other side is, but that's the 8 and the 12. Or the bigger triangle that looks like this, and this side here is really this entire length. That's 10. Again, I don't know this. I do know the bottom side. I know this. It's this entire length, so that'd be a 15. And then I don't know the third side. So I don't think I'm doing side, side, side similarity. I think I'd be doing side angle. Don't they both have this exact same angle? They lie right on top of each other. This angle and this angle are identical to one another. They're angle K. All right, I've got the angle. Let's check the sides being proportional. So is the 8 to 10 going to give me the same ratio as the 12 to 15 does? And again, you can divide it out. 8 divided by 10, that's 0.8. And then 12 divided by 15, well, looky there, that's 0.8. All right, so they are the same. I think what I have here is I have two sides that are proportional, and the included angle, the angle between them, is congruent. We call that side, angle side, similarity. Okay, since we're doing some proving, we might as well throw a proof in there. Let's see if we can prove these triangles are similar by one of those theorems that we had. All right, so we have a whole bunch of given stuff. It looks like they've kind of split it up. We've got these two segments congruent. That's all marked in the picture. We do have this F and J congruent. That's somewhere later. It looks like it's right there. That's given. Okay, so now let's look what else we've got. Why would FGH be isosceles? Okay, well that's because they told me their two legs were the same. And same thing with the other triangle. If two legs are the same, then it's isosceles. That's just the definition of an isosceles triangle. Okay, next, why would F be congruent to H? This angle here congruent to this angle. Why would that be the case? Well, it's because, remember, the isosceles triangle, if two legs are the same, then these base angles are the same. That's called the isosceles triangle theorem. It's been a while back. Good for us to review that. Okay, same deal over here. These two angles are going to end up being the same also. Okay. Now, it told me that F here, this angle, F, is the same as this angle over here. So we could do a lot of transitive or substitution, however you want to call that, where if F and J, well, let's look at how it's written. Right here, I think it's these three. Look at this. If F is congruent to H and F is congruent to J, then H and J have to be congruent. That's classic transitive right there. And then I think we could do it again. Let me change colors. It's going to get messy, sorry. Now I'm going to use this one and these two. Oh, wait a second. I used too much stuff there. I really don't need this one here at all. Sorry. J is the same as L. J is the same as H. L and H must be the same. That's just another transitive. Okay, now what have we shown? All right, let's mark our picture up here. I've got H and L congruent, so this one is congruent to this one. Earlier I scribbled it out. Gosh, what a mess. I apologize. Right there, F and J were the same. Okay, if F and J are the same, well, I just have two sets of congruent angles. We have angle, angle, similarity going on there. We just did it. Prove those triangles similar. All right, let's see what we've got here. This is explain why the triangles are similar. So that's going to be one of my theorems, angle, angle, or side, angle, side, something like that. Then find the distance represented by x. Okay, let's see what we've got. I think why the triangles would be similar. You have this right angle and this right angle, so that's one set of congruent angles. And then you have like vertical angles, so that'd be another set. So I think they're going to be similar because of angle-angle similarity. That's usually pretty easy to show. And then the second part is figure out what x is. And when you set this up to look for a certain side length, you got to make sure that you have like the matching sides lined up properly on these two triangles. So when I look at this, the side that's between my two congruent angles, this side, matches up with this side. So let's set that ratio up. I'm going to go little triangle to big triangle. So 90 over 135 equals. So all the sides should have that ratio right there. So then I'm going to compare that to my 120 that corresponds to my x. So 120 is my little triangle, x is my big triangle. And because I know they're similar, those ratios should hold true. So let's do cross products. So 90x equals 135 times 120. And then divide by 90. All right, comes out nice. X is equal to 180 feet. That's how far across the pond it is. And actually, that's kind of one of the cool things of doing these triangles is that you can find measurements that you wouldn't necessarily be able to find. I mean, it would be hard to measure across a pond like that. So by using triangles, you can find some measurements. All right, let's see if you can do this one. Here's a different scenario. I'm looking to see how tall this clock is. And so there's like this mirror, and you're looking at a reflection of the top of the clock. And so you're setting up your two similar triangles. Again, you've got this right angle on both of them, and it's already shown me that when you're looking down at a mirror, this reflection angle is going to be the same as the angle in my small triangle. So the triangles are congruent by angle, angle again. Can you set up the ratio of the sides and solve that proportion? All right, so go find how tall that clock is. Pause the video, go work through it, and then come back. All right, here's the proportion I set up. The 4 corresponds to the 10, that's small to big triangle. And then the 5 feet 6 inches, I just called 5.5 feet. That's 5.5 feet. Solving for x. Cross products, 4x equals 55. Divide by 4, x equals 1, 3.75. All right, and that would be measured in feet. All right, so here's our last scenario. It says we've got these two triangles. We're going to solve for x, so we're going to set up your matching parts here. It looks like I've got a 37 in the small triangle, corresponds to a 2x plus 10 in the big triangle. And then I go to my hypotenuse there. I've got an x minus 1 in the small triangle, corresponds to a 62 in the big triangle. All right, now I'm going to do cross products. This is going to get messy. Here we go. 37 times 62. All right, got that. That's 2,294. And it equals, the other direction I'm going to have to do FOIL. So when I multiply first, that's 2x and x. Multiply the first, I'm going to have 2x squared. Okay, then I'm going to multiply the outer, so that'd be my 2x and my negative 1. Now multiply the inner, 10 and x. And last would get me a negative 10. Okay, you can see right here when I say what we've been waiting for, here's an x squared. This is going to be one of those ones we have to factor. And that's why we reviewed factoring earlier on. Okay, so we want this to equal 0. We want to combine like terms. I'm going to go ahead and I guess I'm going to clean up. This is a 2x squared, but these two terms can combine, plus 8x. And then the other thing that I can do is I can subtract this 2294 over here with this minus 10. Those are like terms. That way it's going to equal 0. Remember, we always wanted it to equal 0. And then this is going to be negative 2,200. Oops, no, actually, when I combine those, that's going to be 2,304. All right, now, factoring that, oh my goodness, this is crazy. First thing I guess I'm going to do is I'm going to factor out a 2, because I do have a common factor, and that's going to make my life a little bit easier. Factor the 2 out. X squared plus 4x minus, I don't know, let me just type that in so I don't goof it up, 1,152. And somehow or the other, I'm going to have to factor this. All right, I'll do first. You do last. X and x. You figure out the last. All right, so here we go. I don't know really the easiest way to do this, but I've got this 1,152. It's a negative, so my signs are going to be different. I'm going to have two numbers that multiply to each other, but they're not very far apart. For as big as that number is, there's going to be one positive and one negative, and when I combine them, it's going to end up equaling 4. So I've got to find a couple factors that are pretty darn close to each other. All right. One of the things that you can do, I don't know, I'm just going to do some guess and check real quick. And I don't know, I'm going to do 1,152, and I'm going to divide it by 12. Okay, 12 actually worked. Got lucky there. So it's 12 and 96. All right, but they have to have a difference of 4, and those certainly do not. Because remember, one of these numbers is going to end up negative. Okay, but if 12 goes into it, maybe 24 does. So I'm going to do 1,152 divided by 24. Okay, 24 does go into it. 48 times. All right. Still not a difference of 4, so these numbers have to get closer together. So I guess I'll try a 36 maybe? All right, 36 does go into it. 32 times. Looky there. I Can't believe I got that. 36 and 32, those have a difference of 4. I want one of them to be positive and one of them to be negative. Since I want this to end up a positive 4, I want my bigger number to be positive. So my 36 will be positive and my 32 will be negative. So I'm going to put plus 36 and minus 32. And this 2 out here, I really get to kind of, I'm taking 2 times this quantity times this other quantity. And typically what we do is we set everything that's being multiplied, set it equal to 0. So I could do 2 equals to 0. I could do x plus 36 equals 0. And I could do x minus 32 equals 0. All right. The deal with this 2 equals 0 thing, if that was an x with it, I could do something with that. But 2 does not equal 0, no matter what. There's no x there to help me. So I just cross that one off. Anytime you're just pulling out a number for your GCF, it just gets crossed off. And then I get x equals negative 36 and x equals a positive, this is kind of messy, sorry, x equals negative 36, and x equals a positive 32. But if you look back at the problem, does it make sense to let x be negative? Like right here. You'd have negative 36 minus 1, and the length of this side would be a negative 37. That doesn't make any sense. So sometimes in geometry we get these algebraic answers and we have to X them out. They don't work. Now the 32, it's okay for it to be positive. I like it. Solve for it. I got it right there. That is my solution. X is 32. All right, that's what we were doing the practice on the factoring, is to refresh your memory on that. Persevere a little bit here with this. You can come up with those factors. They're not super terrible on Math Excel. All right, good luck.